Welcome. In this lecture, we will discuss projectile motion, satellites, orbits, and Kepler's laws. Projectile motion. Consider a table, and on that table we have a ball. Let's make a reference frame. The x-axis is horizontal, the y-axis is vertical. If we ignore gravity and air resistance for a moment, and I roll this ball off the table, and we take pictures of the ball in evenly spaced increments of time, the ball's spatial distance will be equal. And that's because there's no acceleration. It's going the same speed from left to right. If I bring back gravity and I drop the ball off the table and take snapshots at equal intervals in time, the spatial distance between the balls will no longer be the same because there is acceleration. Closer to real life, we will have the superposition of horizontal motion and vertical motion. So what will that look like? Well, let's bring back our horizontal snapshots. Let's make a grid. In real life, if I roll the ball off the table, you expect it to take a path that is the superposition, or the sum really, of these two paths. And what does that look like? It looks like this, where it follows a parabolic trajectory. This is known as projectile motion. Now consider a girl who's throwing a ball, or a rock. Draw our reference frame again, throws the ball, or the rock, with some velocity v, and it has some components along our reference frame's axes of vx and vy. Let's ignore air resistance here, so the only force acting on the rock is gravity. As the ball moves up, the direction of the velocity changes, but the horizontal component does not change. It stays exactly the same length and direction. Of course, the vertical component stays the same direction as well, but notice the length changes. Well, why is that? Because the gravitational force is downward, creating a downward acceleration. So the vertical component of velocity will change as the ball moves. At the top of the trajectory, there is no vertical component of the velocity. It's exactly zero. So the resultant vector is only the horizontal component. As the ball goes back down, the direction angles downward of the resultant velocity, and the resultant velocity is simply the sum of the two components. The x component, which remains the same still, and now the vertical component, which is now oriented downward. At another point, the resultant velocity again is getting longer. It's the sum of both the horizontal component, which has not changed, and now the longer vertical component that is downward. And it continues. This is a parabolic trajectory, and this is what we expect when we throw a projectile. Hence, this is called projectile motion. As a reminder, the velocity, the resultant velocity, which is denoted in purple here, is simply the sum of the components, vx plus vy. If we want the lengths of these pieces, we can write this as a right triangle and then write out the Pythagorean theorem. V squared equals vx squared plus vy squared. Let's consider a cannon. If the cannon shoots a ball, neglecting air resistance, it will follow this nice, idealized parabolic trajectory. But if we include air resistance, we must remember that air resistance is a force, and it's always going to be opposing the ball's motion. Because the force opposes motion, it does negative work on the ball, stealing the kinetic energy. Remember the work energy theorem from a previous chapter. So the force does negative work on the ball, therefore it steals the kinetic energy and makes the actual path of the ball short of the ideal path. Satellites. If we take Earth and mark the center of it with an X, which will correspond to the center of mass, and then we put a cannon at some point on the Earth, and this cannon fires a projectile. If it fires a projectile at some speed, but not super fast, but still not super slow, it will launch out of the cannon and crash into Earth. Now what would happen if the cannonball could go straight through the Earth? It would follow this elliptical path. What if I shoot the ball, or the cannonball faster? It will crash into the Earth again. But if the cannonball could go through the Earth, what path would it take? It would take a different elliptical path, a larger one, and so on. We see the same thing. So what we see when we throw objects and they follow projectile motion is that these projectile motion paths are really just pieces of what would otherwise be a fully elliptical path. And we know that the faster you throw it, the further it goes. They all fall into Earth in the example so far because they're not moving fast enough. But what if you throw a ball or shoot a cannonball so fast that it falls, and instead of falling into Earth, it falls around the Earth? So it keeps falling, but it never crashes into the Earth. Now that's only possible if you can shoot something fast enough. This is what a satellite is. It's a projectile that falls around a planet or an object rather than into it. Now the speed of a satellite must be great enough, again, to ensure that the falling distance matches the planet's curvature at minimum. The Earth's curvature is such that a satellite, at minimum, must travel 8,000 meters per second, if we're near the surface of the Earth, in order to actually fall around the Earth rather than into the Earth. That's an extraordinary speed. That's 8 kilometers per second. That is no joke. Now, realistically, if something were traveling that fast in atmosphere, it would burn up. The air friction would completely burn up the object. But if we ignore air resistance, then an object could actually fall around the Earth if it were traveling 8,000 meters per second. Let's talk about circular orbits. Consider a satellite. So this satellite is falling around the Earth, but it's falling in a perfectly circular path. What's keeping it in this path? Well, the force of gravity. The force of gravity is keeping it here. It's pointed toward the center of the path, which means that the force of gravity is the centripetal force here. And that produces a centripetal acceleration. And the centripetal force is completely perpendicular to the velocity. So the satellite will follow this motion shown here in the animation. Now, what are some properties of circular orbits? One, as I already mentioned, the gravitational force is completely perpendicular to the velocity, which means it's completely perpendicular to the direction of the displacement. What does that mean? Is that no work is done on the satellite by the force of gravity. So there's no change in the kinetic energy because no work is done. That means the change in the speed is exactly zero. Speed doesn't change. So at every point along this circular path, the speed of the satellite is the same. The kinetic energy is the same, the speed is the same, the potential energy is the same, everything's the same along the circular path. And why do I point that out? Because in an elliptical path, that is not exactly true. Though energy is still conserved in both a circular and an elliptical path, there are definitely some differences. Notice here that the gravitational force is no longer at a 90-degree angle to the velocity vector. So that means there's a component of the gravitational force along the velocity vector and a component perpendicular to it. We can go to another location on the path and see that here's the gravitational force, here's the velocity, and again, there's a piece of the gravitational force oriented along the velocity and a piece perpendicular. What does this mean? It means that the gravitational force, because a piece of it is oriented along the direction of the satellite's displacement, that the gravitational force does work on the satellite. If it does work, it means that it changes the kinetic energy. If it changes the kinetic energy, it means it's changing the speed of the satellite, which means that at different points along the path, there will be different speed. At some points it'll be really fast, at some points it'll be really slow. The point nearest the Earth is where the satellite will have a maximum kinetic energy, which means it's moving the fastest here. The point farthest from the Earth is the point at which the satellite has the maximum potential energy, and therefore the minimum kinetic energy. So it moves the slowest here. Now at every point along the path, though the kinetic energy differs at every point, the sum of the kinetic energy plus the potential energy is equal at every point along the path, because energy is conserved. Energy is conserved in all orbits. Keplers laws. Now we've already talked about an ellipse, but I haven't really defined what it is. I've just shown you a picture of it. So what exactly is an ellipse? Let's consider 2 points, F1 and F2, and these will come to be known as the focal point of an ellipse. Then take another point, P, and draw lines to P. And the sum of the distances of these 2 pink lines will equal some value, whatever that value is. Now the question is, are there any other points like this? Meaning that, are there any other points that I could put on this slide where if I add the 2 distances together, they will produce the same value of what adding the 2 pink lines together produces? The answer, of course, is yes. I can put a point here, and I'll call it Q, and draw 2 lines to it. The sum of the orange lines will produce some value equal to the sum of the pink lines. Is there another point like this? Sure. Call it X. Now we have 2 teal lines. So if I add the lengths of the 2 teal lines together, that will equal the same value as if I add the lengths of the 2 orange lines together or the 2 pink lines together. And there are actually many more points like this. There are an infinite number of points like this. And the collection of all such points is an ellipse. An ellipse is more general than a circle. if we were to place F1 on top of F2, then we would get a circle. So a circle, and I don't have an animation for that, but a circle is just a special form of an ellipse. So every circle is an ellipse, but not every ellipse is a circle. Okay, so let's consider the sun is at one focal point, and the Earth is orbiting elliptically. Now the Earth realistically is more close to a circular orbit. It's not very elliptical. It's very, very close to being circular. But I've kept the animation like this simply because all the other planets in the solar system follow much more dramatically elliptical paths. Now Kepler's first law says that the path of each planet around the sun is an ellipse with the sun at one focus, or one focal point as I've called it. Now, to get to the second law, let's consider where the Earth is now, and then let's say some time later, some month later or something, some time interval later, whatever the time interval is, the Earth is now in a new location, and it's traveled some arc length as shown by the orange line. Now, using that same time interval, when the Earth is closer to the sun, it will travel a larger arc length because its kinetic energy is higher, meaning it's moving faster. So it'll travel this whole distance. So the time intervals are the same, but the arc lengths are different. But there's something else that's the same. So arc length is different, time interval is the same. What else is the same? These two areas. So these two shaded areas that I've drawn, the areas of these are the same. This is exactly Kepler's second law. The line from the sun to any planet sweeps out equal areas of space in equal time intervals. Now let's consider again the ellipse. Define some different parts of the ellipse. C I will denote as the center. Here's the center of the ellipse. These lines I've drawn, are the semi-major axes, and B, each of these B's is a semi-minor axis. Now why am I introducing these terms? I'm not going to spend too much time on it, but it's going to relate to Kepler's third law. Let's put the mass of the sun at one focal point, just as we had before, and the Earth at some point along the ellipse. Now there's a relationship between how long a planet takes to orbit the sun, which we will call the period. Remember from previous chapters, the period is the time required to make one full revolution. So there's a relationship between that period and the semi-major axis. And that relationship goes like this. The period squared equals 4 pi squared over GMS times the semi-major axis cubed. Now 4 is a constant, pi is a constant, g is a universal gravitational constant, ms is just a placeholder for the mass of the sun. If I rearrange this equation, I can write it like this. T squared over a cubed equals, again, 4 pi squared over gms. That's saying that the period squared over the semi-major axis cubed equals some constant value. Now this is actually Kepler's third law. The square of the orbital period t of a planet is directly proportional to the semi-major axis a, meaning the ratio is the same for all planets. Now that doesn't mean that the period is the same for all planets or that the semi-major axis is the same for all planets. What it's saying, which is phenomenal, is that the square of this period divided by the semi-major axis cubed, that ratio is constant for every planet in the solar system. Even though the periods are different and the semi-major axes are different, the ratio, as shown here, equals a constant. Summary. We've discussed projectile motion, satellites, orbits, and Kepler's laws. I'll see you next time.